When you study mathematics, you usually start off by defining a number of concepts. But even before you do that, you have to rely on some undefined concepts. And a set is going to be one of those undefined concepts. So we're going to take the point of view of naive set theory. We're not going to define a set. And you might think this is kind of strange. I mean, why don't we just go ahead and define it? Well, it turns out in mathematics, it's impossible to define everything. You have to have some undefined concepts. And we've chosen a set to be one of those undefined concepts. But we're hoping that if we just specify a set, that you'll have a reasonable idea of what's in that set. For example, the set of integers. You probably know what things are in the set of integers and what things are not in the set of integers. But we will see some problems here. How about the set of letters in the English alphabet? Okay, you probably have a good idea of what that might be. Does it include lowercase and capital? You have to really specify the set. How about the set of dogs in the state of Kansas? Does that mean right now? Does that mean 100 years ago? Does that mean 10 minutes ago? I mean, these answers could all be different. How about the set of some books? Well, this is really a problem. Some books? Which books? Whose books? How many books? So in order to define a set, we really want to make sure that our set is what we say is well-defined, meaning that if you look at an object, you can say definitively whether that object is in the set or whether that object is not in the set. And even that causes some problems, but to really explore this idea, you would need to take a class on set theory, and we're not going to worry about that here. For our purposes, we're going to assume that you can understand the concept of a set and that our sets will be well-defined. Let's look at some examples of sets. So these are examples that you will commonly see in your study of mathematics. So how about the set n? This is the set of natural numbers. It's like the counting numbers, 1, 2, 3, 4, 5, and so on. And I should also specify that when we have a set like this, we use these curly braces to denote a set, and then we can write the things in the set just by placing them in the set with commas in between. And these things that are in the set, we call these the elements of the set. Okay, let's look at another example. How about the set of integers? Okay, this is probably another set that you're familiar with. How about the set of rational numbers? Okay, so now we see a set defined a little bit differently. Here we have the curly braces. Well, we're not actually listing the elements in the set. We're giving a condition to sort of specify what the things in the set are. So you read this as m over n such that, that's what the bar means, such that m and n are elements of z. So this symbol right here, that means are elements of. So if we look at this set up here that has a, b, and c, I could say if this is a set S, I could say that a is an element of S. And I could also say that D is not an element of S. And we want all m and n that are integers such that n is not equal to 0. And these are the rational numbers. These are things like 1/2, or 4 over 1 would be another example, or 6 over 5. But we don't want something like 3 over 0 because remember, n can't be 0, so not that. Okay, what else do we have? How about the real numbers? The real numbers are probably the ones that you're the most familiar with. These are just the numbers that you typically deal with in your high school algebra class. And we're specifying them here as a decimal. So the way you read this might be kind of hard to understand at first. x1, x2, x3, all the way up to xn, these are numbers between 0 and 9. And I should have probably specified here that this xi and yj here refer to the numbers 0, 1, 2, 3, all the way up to 9. So the integers between 0 and 9. And then I have a decimal point, and then I have y1, y2, y3, and so on. So something like 65.44032 would be an example of a real number. And in this notation here, this stuff after the decimal point, these are all the y's, And the things before the decimal point, these are all the x's. So if I want to, I could call this x1, I could call the 5 x2, I could call this 4 y1, I could call the second 4 y2, the 0 y3, and so on. So this is just a way of specifying real numbers in terms of decimals. Okay, complex numbers. Now this is where we take the real numbers, but we add now this thing I, which you probably know as the square root of -1, so that I squared is equal to -1. And it's numbers of the form a plus bi, where a and b are both real numbers, and I squared is -1. That would be something like 3 plus 2i. So in this case, the 3 would be the a, and the 2 would be the b. Okay. So those are the common sets that you'll see in mathematics, but let's look at a few more examples. How about 2z? What's this? Okay, so this is where we take the set of integers and sort of multiply it by 2 in a sense. In other words, we're going to look at all things of the form 2n such that n is an integer. So that would be something like, if we start from the negative n, -3 would not be in it, -2 would be in it, -1 would not be in it, 0 would be in it, 1, nope, 2, yeah, that's good, 3, nope, and so on. And you see why this works here. So why are we writing it like this? Well, -2 is the same thing as 2 times -1. This is playing the role of n here, -1, and -1 is an integer, so that works. How about 0? Well, 0 is the same thing as 2 times 0. Again, the 0 will be playing the role of the n in our definition, so that works. How about the 2? 2 is the same thing as 2 times 1, where the 1 is playing the role of the n now. So you see how this works, and we don't have to do it just with 2. You can also do it with 3. So this would, in essence, take the integers and multiply them by 3. So maybe just to write a few of these elements out, I won't write the ones that aren't in the set, I'll just write the ones that are in the set. So in this case, we might have things like -9, -6, -3, 0, 3, 6, 9, and so on. Okay. R with a little plus sign. So this just means take the real numbers and only look at those that are greater than 0. So 0 is not in this set, but everything else that's greater than 0 is in the set. So 1 is in the set, 1.1 is in the set, 200 is in the set, 4/5 is in the set, but -2.3 is not in the set. How about if we want the numbers that are real numbers that are greater than or equal to 0? Well, then we use the greater than or equal sign as a superscript on the r here. So that would include all these things along with 0. We could do the same thing with the integers. We can look at all of the integers that are greater than or equal to 0. So that would be 0, 1, 2, 3, and so on. And then we have z star. This would be all the integers that are not equal to 0. So that's pretty much all the integers but 0. So we can start at the negative end here. We could have -3, -2, -1, not 0. We're not going to include that. 1, 2, 3, and so on. And of course, you could always do this with other things, like the rational numbers, or I could say the real numbers with a little star. I mean, all the real numbers except for the element 0. So I'm just giving a few examples here, but you might interchange these r's and z's with other sets that we've already talked about. The empty set, which is denoted by this circle with a line through it, is the set with no elements, and that's a very special set. And I say the empty set is the set. There's only one empty set, and it's the set with no elements in it.